Greetings, everyone. This is Rifat Sipahi from Northeastern University in Boston. I'm a faculty member here at the Mechanical and Industrial Engineering Department. And today I'm joining you to present you some insights into frequency domain techniques towards analyzing the stability of a class of time delay systems, linear time invariant systems. Thank you for joining me, and I look forward to presenting these slides and hopefully eventually interacting with you for any questions. Let's get started. Before we even get started, please allow me to thank workshop organizers, in particular the General Chair, Publications Chair, and Workshop Chair, Professors Krishna, Ibrahim, and Mark. And of course, all of you participating and spending time here with me today in this workshop. And why time delays? This is where I would like to start. And maybe I'll start with a claim, and then I'll do my best to convince you that many dynamical systems, the events in these systems unfold based on what has happened in the past. And what does that mean specifically? And as an example, what I mean is that what happens in a dynamical system at time t can be affected by a historical event that took place earlier at time t minus tau. Here, the positive quantity tau is known as the time delay, or sometimes we just say delay in short. When this historical event happens at a point in time at t minus tau, we call this type of delay as discrete delay. Is a schematic representation of that, where we see now being time t, right, is being influenced, its fate is being influenced by some event that has happened in the past, tau amount of time ago, and that event has an influence on the dynamics now at time t. I have a good number of examples, and here are two examples to provide you some sense of what this may look like, these delays. Consider a hot rolling problem. And this is a very typical manufacturing process where two rollers squeeze a metal plate to reduce the plate to a desirable thickness. And obviously it's hot, meaning the metal has to be hot enough to be able to allow the rolling to easily happen. So imagine that we want to control the thickness of this plate. And for that, we will first need to measure the thickness. Second, we need to act on the rollers to tell the rollers to squish the metal more or less towards achieving a particular thickness. However, the sensor cannot handle high temperatures. So to protect the sensor, we'll have to place the sensor downstream of the process where the metal leaves the hot area and starts to cool off. And then those low temperatures will not damage the sensor. So the sensor, although being in a safe location, will be measuring the thickness downstream of the process, and this thickness is actually a thickness that was achieved by the rollers tau seconds ago, before the material has reached the sensor. Now the sensor measurement can be used to inform the rollers in terms of how much more to squeeze the material, and on the other hand, this measurement is not an instantaneous measurement. It is a measurement that has happened in the past. Another example is information transmission delays. Consider a scenario where a robotic system, say at a site 1, must be remotely controlled from a site number 2. And in this case, site number 2 must be aware of robot states, and for that, robot states measured at site 1 must be transmitted over some communication medium to site 2. but this transmission is subject to a finite transmission time. It cannot happen instantaneously. Therefore, by the time site 2 receives the information, it only knows what the robot states were tau seconds ago, and during that tau amount of time, the robot has actually moved and its states are in a different location and different configuration that we are not aware of. There are other examples where delays can actually be what we call distributed over the past. And this is a case where we can consider a continuous collection of events from the past, all collectively contributing to the fate of the dynamics at the present. And in this case, here in the schematics, what we see is a distribution determined by some function f eta. And we can consider that to be some type of a weighting of the relative importance of the past information at any delay values between t minus tau to t minus h. And all these effects collectively under the integral term will then contribute to what's happening right now. And thus the distribution of that information affecting from the past the current state, these type of delays are called distributed delays. Here are two examples. One is a famous example from machining process, a commonly known phenomenon called regenerative chatter. And in this metal cutting process, chatter, an undesirable phenomenon, happens in part due to the time delay. Delay in this case is actually the cutting tool tooth passing period. And the tool that is cutting the metal encounters cutting forces at time t as a function of material's thickness. But this material thickness is in part determined by what was uncut in the previous cutting cycle at time t minus tau. Therefore, the cutting forces on the tool are in part influenced by what has happened in the past. And because the force should be produced by integrating the pressure over the cutting tool, this leads to a distributed delay. Another example is human car driving, acknowledging that humans have reaction times and therefore they cannot react to events instantaneously, but only after a certain time has elapsed. One suggestion is that humans have continuous experiences over the time horizon, and therefore their actions could depend on a collection of events that occurred in the past. Under this assumption, one can then model the human memory using distributed delays. Other examples, some of them I actually referred to, include remote surgery, postural control, inventory control, car following dynamics with human reaction delays, and network control systems. Now, if you go back in the remote surgery case, as I mentioned, one idea is having two different sites with different capabilities or skills and technology developments, where transmission times between the two sites will be subject to, will cause delays. And these delays can be in the form of force feedback from one side to the other, to the operator to the left, from the right-hand side. It can be a video feedback that can also be subject to delays. In the postural control, one will find delays in the human neurological system and the amount of time it takes to transmit information between the ankles and the brain. And in inventory control, there are delays in manufacturing, in transportation, and sometimes decision-making delays. In inventory control problems, we see time delays. And human reactions, as we said, are not instantaneous. Therefore, car driving with humans is actually a time-delayed system. And network control systems is similar to the first example here, where there may be delays between the cloud or the remote site or a sensing device that has to transmit information over different geographic locations. To summarize, we can say that there are maybe four or five main reasons we can think of where delays are influential on the fate of the dynamics, because it takes time to transmit information from one location to another. It takes time to process any incoming information towards formulating a decision. It takes time to sense and measure a physical variable. It takes time to ship or move products between supply points. And it also takes time to mature or incubate, as seen in biological systems or in epidemiology. And obviously some combinations of the above can appear in the same dynamics as well. The last item 5 is one I haven't really described earlier. This would, for example, refer to a situation where an individual or a biological system may be subject to a virus, but they will not become infectious until a certain amount of incubation time elapses. And or a biological system will need to mature first before they can produce offspring. These are some examples that we would find in population dynamics, for example. There is a large array of publications, including books in the literature. This is just a very small snapshot, and because I'll be also drawing some examples from my textbook, I also put my book at the bottom right. And but depending on the type of technical questions one is wishing to answer, some of these books would be a good starting point. And of course, the literature is a rich amount of resources in terms of application areas, mathematical results, and theory, and experiments, and a variety of engineering problems. Let's start talking about delays and start putting some equations to this effort. And let's take a very simple differential equation as shown on the top left here. Dx dt is equal to ax plus u, and imagine u is some type of an input, and that input depends on the delayed state of x. So we can imagine that this is actually a first order system, as we see here, subject to an input, but this input is not aware, for some reason, is not aware of the instantaneous measurement x of t. It can only access what x was tau seconds ago, and then multiply by some constant b, some weighting, right, or some controller gain, imagine, proportion controller, and creates the signal u that is then fed into this system to derive this system. And so from this point onwards, for the rest of the workshop, I'll focus on linear time invariant systems. And so in this case, a and b are constants, and they are time invariant. We have a linear system in x, as you can see, and again, delay is also a constant. Let's see what happens. Some of the questions we may want to answer, depending on how the problem is posed, are as follows. For example, we may be given a and b values, and we may be wondering what delay values, for what delay values we can maintain exponential stability of this system. Or we may be given a delay value, and we may wonder what combinations of a and b will render this dynamics stable. Or maybe we are given only a, and we wonder what b and tau combinations will achieve exponential stability. I put the exponential here in the parentheses because without losing any generality, I will keep saying stable, and I apologize if I do that. And every time I say stable, actually what I mean is exponential stability. And for linear systems, we know that asymptotic stability implies exponential stability. And but if I say stable, what I mean is exponential stability. All right, what is the starting point to be able to answer these questions? Well, just like we would do when there are no delays, right? Why don't we take the Laplace transform and investigate system stability through the system's characteristic function, f. Since initial conditions don't affect stability determination, we set them to 0, take the Laplace transform of these two equations, and we'll arrive at this characteristic function. Notice here that because of the time shift operator in time domain on the top left, right, the Laplace transform of this xt minus tau will be exponential minus tau s times x of s. And therefore, you see this exponential function here representing the effect of the time shift. And when the delay is 0, we recover the standard linear control problem, which we are very familiar with, right? We can equate this function to 0. Then we'll have s minus a minus b is equal to 0. And we can find s is equal to a plus b. And if a plus b is negative, the system is stable. When the delay is not 0, there are some problems. There are a lot of problems, actually, because this delay multiplies the s term, which we want to solve. So now if delay is not 0, equating the equation to 0 and trying to solve for s is in general difficult, or in many cases impossible. And because of the exponential function, this equation actually has now an infinite number of roots. Therefore, when it becomes an equation equated to 0, it will have infinitely many roots, and it is actually impossible to solve all these roots. And in the following slides, what I want to do is I want to give you a little bit more background and some foundation and some scenarios one may expect, and before we become more technical. All right, let's move on. Of course, we don't have to have scalar problems, as in the case here. We may also have state space problems, so multidimensional problems. Here's an example where X is a vector of states. A and B are n by n matrices. We have n number of states. And this is a linear time invariant time delay system. A and B are constant matrices. Delays, tau is also constant. And we call this system a retarded type system because the highest derivative of the state is not affected by the delay tau. There is no tau inside x dot. Here's another example where this time the highest order derivative of the state x dot is influenced by a delay tau. These type of systems are called neutral type systems. And there is obviously a very clear and important distinction between retarded and neutral type systems. In a moment, I'll explain you with an example what I mean. And here's another example where we may have actually two different delays, tau 1 and tau 2. Maybe we have two different sensors, and that may impose different delay values into our dynamics. Who knows? And all right, let's try to a little bit more understand what's happening here between retarded and neutral systems. And then once we establish that, we will stay away from neutral systems and then just focus on retarded type systems, because actually most of the things I will present with care, they can be also applied to neutral systems anyway. So let's take a look at two examples. They look very similar. Here's a retarded type linear time invariant system where x dot doesn't carry any delay terms. And here's a neutral type system on the right hand side where x dot carries a delay term tau. All right, so let's obtain their characteristic equations. So retarded system has a characteristic equation of this form. Neutral system will have a characteristic equation of this form. All right, we equate those two to 0. Okay, all right. So let's go back to our linear systems classes where we didn't have to deal with delays, right? So let's remember that first as our maybe baseline. Set the delay to 0 and solve for s. On the left-hand side, the retarded system has one pole at -6 because it's negative. Its real part is negative. This system is stable when there is no delay. delay-free system, zero delay case is stable. Likewise, a neutral system is also stable when the delay is zero because its single pole is on the left of the imaginary axis on the complex plane. Good. That's very easy to establish. Now, what happens if I perturb the delay just a tiny bit? Imagine that I have an infinitesimally small delay, tau 0 plus. A retarded type system, whatever its stability property is for delay 0, will maintain that property when the delay is sufficiently small. If it's stable, it will remain stable. If it's unstable, it will remain unstable. Whereas a neutral system does not always follow that rule. In other words, its stability, instability characteristics may not be preserved under small variations of delays. This is very counterintuitive, but it is the case. So in this problem, if you were to perturb the delay just a tiny bit, the system actually becomes unstable. And as a matter of fact, for any positive delay, no matter how large or small, the system, this neutral system will be unstable, even though for zero delay, it was stable. In other words, neutral systems do not necessarily preserve their stability, instability features from zero delay to zero plus delay. All right. Now, what about another problem of neutral type? So instead of 4, we change the gain to 0.5. Characteristic equation becomes as shown, and zero delay, the pole is negative, therefore zero delay, the system is stable, like in the previous case. But this time, the stability property will be preserved. When the delay is slightly larger, the system will still remain stable. So clearly here we have two examples of neutral systems, one in which the stability property is lost because of some discontinuity that happens here as the delay transitions from 0 to 0 plus, whereas in the other one, that discontinuity property doesn't arise and stable system remains stable under small variations of delay. This issue does not happen in entire systems. If they are stable for zero delay, they will remain stable for 0 plus delay. If they are unstable, they will remain unstable. The stability property will mirror from 0 delay to 0 plus delay. All right, what's the catch here? Let's try to explain that. Before we explain that, I may interchangeably use these terms, and just to clarify, when I say roots of the characteristic equation, s equals minus 6 is the root of the characteristic equation. And these roots are actually the eigenvalues of the dynamics. They are the same thing. And these roots are also known as the poles of the system. All right, so if I say roots, eigenvalues, or poles, I'm actually referring to the same thing. And all right, so what's the catch here with neutral systems? Now, we have that for retarded type systems, whether they have single or multiple delays, their poles or eigenvalues, they follow a continuity property on the complex plane with respect to delay and system parameters. And for that reason, as delay, for delay 0, if they are stable through the continuity property, we know that there exists a very small delay, non-zero, for which stability will still hold. Neutral systems do not necessarily respect this rule. And here's an example for a single delay example. And for neutral systems, an additional condition must hold for the stability property to exhibit some type of a continuity principle. For a single delay problem, a neutral system of this type, right, will have to have its C matrix to have its spectral radius less than 1. If that is the case, zero delay stability will be preserved when the delay is perturbed. If that is not the case, although zero delay system is stable, zero plus delay, it will be unstable. This is the reason in the previous example, the first example failed, because 4 representing the scalar version of the state space equation here in place of C matrix. We have 4 here, and 4 is not less than 1. Therefore, this system will not exhibit a continuity property in stability characteristics from zero delay to zero plus delay. Whereas the other one does, because 0.5 is less than 1. For that reason, although the left-hand side system is stable for a zero delay, it will be always unstable for any non-zero delay. Whereas the right-hand side is stable for a zero delay, and it will be stable for a zero plus delay. That's something that we know. All right, so just remember that when you are dealing with a neutral system, there are additional conditions you need to double check before you can conclude on stability analysis. But these conditions are well established, and so from this point on, I will not spend time on neutral systems. I will just focus on retarded type systems. There are other systems, for example, certain class of partial differential equations also exhibit neutral type behavior. And there are other systems that may look like a retarded system when you inspect them, but they are actually spectrum. Their eigenvalues may behave like a neutral class system. So just want to caution those that are starting to maybe get into this field to pay attention to the class of differential equations they are actually dealing with, to make sure that all the conditions are carefully checked to complete the stability analysis. All right, moving forward, we are actually scoping this presentation to retarded type, linear time invariant, time delay systems. Obviously, we're going to start with problems with single delays. If time permits, we will maybe demonstrate a multiple delay example, and that's how we will conclude this workshop. All right, so now let's take a look at open loop versus closed loop. So imagine we have a transfer function g of s, and a signal comes in from left, goes out of GFS, subject to a delay tau. We are obviously talking about LTI systems, and delay is also constant. And in this case, imagine delay is modeled as a discrete delay. Sometimes it's also called dead time. And it means if there is an inflow coming into this delay box, the outflow is going to be a time shift. Without distorting or changing the shape of the waveform, the waveform will get out of this delay box with a pure delay or time shift. In this setting, imagine we have x of s as the input, then the output of the delay box is going to be x of s times g of s times the delay operator, which in Laplace transform becomes exponential minus tau s. In this setting, this is an open loop system, and because there is no feedback from the output of the delay back to the g of s. And in this case, there is no concern of instability, because this is an open loop system where, if, in other words, if x of s is bounded, the output of the delay box is, and if g of s is stable, strictly stable, then the output of the delay box is obviously going to be stable. It will be just time shifted by tau. That's it. Nevertheless, if the delay is in the feedback line, then that actual delay can cause instability. Because in this case, what will happen is the output being delayed and fed back to the controller, and potentially that controller signal will be transmitted with a delay, and this delay in the feedback line can actually throw off the stability of the system, as I intend to demonstrate in the following slides. All right. So now, scoping a little bit more, we're going to look at closed-loop systems. When we deal with delayed closed-loop systems, we may actually run across some interesting results. For example, what we call stability maps in one-dimensional or two-dimensional planes. Here's an example where the horizontal axis can represents the amount of delay in the closed-loop system, imagine. And the vertical axis, let's say, represents a feedback control gain, maybe a proportion control gain K. In some problems, it may happen that we have actually stability independent of delay. For example, if the gain is sufficiently small, no matter how large the delays are, the system can always be stable. And the system may exhibit some delay-dependent stability, meaning for larger gains, it will have some stability interval for some delays up to a certain margin, which we call delay margin. But for larger delays, the system will be in the unstable territory. And so another example could be a one-dimensional stability map, where one may find, although it may be counterintuitive, one may find multiple stable intervals along the delay axis, meaning the system is stable from 0 to tau 1, and it is also stable from tau 2 to tau 3, as an example. And this is a one-dimensional stability map. This one on the top left is a two-dimensional stability map. So one of my objectives will be to present and teach how these stability maps can be extracted from a closed-loop system subject to time delays. What other examples can there be? There can also be examples where both axes are delays. For example, delay 1 maybe represents sensor 1, and delay 2 represents sensor 2. In these cases, one may find with these dotted areas multiple stability regions. It is possible that there will be stable regions. They are disconnected from the origin. In other words, two stable regions are separated by an unstable region, the white region, without the dots. And in some dynamics, we will actually reveal, we'll come across these disconnected stability regions. Now, the advantage of stability maps is that they give us a visualization of which delay pairs are good, which ones are bad. In other words, they are destabilizing. They can also allow us to perform parametric studies. For example, we can change maybe a parameter of interest and see how these regions actually shape and distort and maybe enlarge or shrink. And of course, in certain problems, and this is something we have shown experimentally, one can add artificial delays in the feedback line with intention to land on a stable region from an otherwise unstable territory. Imagine your delays are 1 and 1.5, and you know you'll be unstable. Why not add an intentional delay in the feedback line so that you configure your delays to be in a stable region? This is something that can be done. And of course, the literature is very rich with a large number of publications on these topics and from a variety of technical aspects. Why don't we go over an example to demonstrate what is happening? So here's a very simple system where the controller is a proportion controller K constant. The system, the plant H in this case, is integrated dynamics, and the delay is obviously exponential minus tau s in Laplace domain. And what we want to understand is this system going to be stable? Of course, stability depends on what the value of K is, what the value of tau is, and we want to understand the interplay between them when it comes to studying stability. All right, so let's take a look at this problem. Some of the questions we may want to answer is, if I know the controller gain, can I compute the amount of delay that I can tolerate in my closed-up system without becoming unstable? On the contrary, maybe I know the amount of delay in the feedback loop, then I want to select a gain K such that the system is stable. And in some problems, this is possible. I may wonder whether or not there is some amount of gain K I can use that will render the dynamics stable regardless of how large or small the delay is. In other words, can I achieve delay-independent stability if I were to choose a gain within a certain interval? These are some questions one may wonder. All right, let's obtain the closed-loop system transfer function, which reads as follows. And here are 3 simulations. We are not analyzing anything yet. We are just experimenting with time simulations. Obviously, I set this up to be able to demonstrate to you, and there's a reason why I chose a gain as pi over 4, pi over 2, and pi. The delay in the feedback line is 1 second. And if you simulate the system for different gain values, we see characteristically very different behaviors. The first one representing against the unit step input, a stable behavior despite 30% overshoot. The second example where the gain is cranked up is increased by twice, the first one. The system, although receives a unit step input, it actually produces sustained oscillations. And if the gain is larger, in this case is doubled again, the system output actually diverges from 0. The system becomes unstable. So these type of behaviors we are actually very familiar with from linear control problems and in the absence of delays. And so some of the interpretations actually will mirror from that knowledge. The first system, in the first case, the system is asymptotically or exponentially stable. The second one is marginally stable. The third one is unstable. And this behavior these 3 characteristic behaviors are obviously governed by the characteristic equation, characteristic function, and what the characteristic roots are. If all the roots of the characteristic equation, in other words, take the characteristic equation function, equate to 0, imagine you can solve S from this equation. You can solve all the S values for the given K and tau values. And if you notice that all those S values have negative real parts, in other words, they are on the left half of the complex plane, then we know that the system is stable, and therefore it will produce a stable step response. If the system has a pair of imaginary roots, obviously on the imaginary axis, and all the remaining roots are stable, meaning they lie on the left half of the complex plane, then we have a marginally stable system, and because of those imaginary roots, the system will produce, in steady state, sustained oscillations. If there exists at least one root or one eigenvalue of the system with a non-negative real part, then we have an unstable system. This is how we can explain the time responses as a parameter of system eigenvalues configuration on a complex plane. In other words, system spectrum, right, determined by the characteristic function, helps us actually identify what type of time response do we expect. We don't talk about stability. We're not talking about performance in this presentation. So I'm right now really looking at whether or not I'm stable and what is the critical value, in this case pi over 2, that separates the behavior from instability. All right. How do we find these roots? Right? Clearly, we need to compute these roots to determine whether or not the system is stable. But earlier, if you recall, I mentioned that because of the presence of delay, and then the delay appearing in this exponential function, we have a transcendental equation, meaning this characteristic function equals 0, has infinitely many roots S. So how can we make this decision if we are not able to compute all of these S values? There are infinitely many of them. In general, it will be impossible to compute all of them. So how can we decide on stability if we can't compute all of them? Well, the good news is there is a couple of good news. One of them is we actually just need to compute the rightmost roots, because those are the ones that are closest to the instability boundary. Rightmost roots, if they are stable, meaning they have negative real parts, their distance to the imaginary axis is a measure of how stable we are. So we actually don't need to compute all the infinitely many roots. We want to make sure we compute the rightmost roots. And there are ways to compute them. Here's an example, not related to the previous example. Here's a different example where I show as delay value changes, we can actually compute the system poles with these blue markers using BEEF tool. So as we increase the delay value in the system, the eigenvalues of the system marked with the blue markers, right? They actually migrate on the complex plane. For retarded type systems, all of these eigenvalues will actually arrive from negative infinity, and they are not visible in the scale. And when the delay is zero, we have only a finite number of poles, imagine. But as the delay value is increased, those eigenvalues that actually depart from negative infinity real part, they will eventually penetrate into this finite complex plane domain, where they will become now visible in the range we are inspecting the complex plane. So all of these, most of these roots, except these three, they actually arrive from negative infinity due to the transcendental nature of the delay of the characteristic equation imposed by the delay. As the delay value is increased, these eigenvalues actually are migrating on the complex plane. They don't have to go to the right. Sometimes they can go to the left, but they are moving around as delay is changing. And there's going to be some critical delay value for which they will touch the imaginary axis. When they touch the imaginary axis, we know that we are losing stability. When they touch the imaginary axis, we know that we are actually recovering this green curve, because the marginal stable means all the eigenvalues are stable except 2 on the imaginary axis. So the bottom line is the touch of the imaginary axis, touch of the system eigenvalues on the imaginary axis for some delay values is extremely important, because this is when we are losing stability. We were stable before for smaller delays, but as the delay touches some critical value at some critical points on the imaginary axis, we are no longer stable. So it's actually for that reason, it's really important to investigate linear time invariant time delay systems where for their poles on the imaginary axis for some critical delay values. All right, what are some ways of let's summarize this, and then we can then have a formal example to look into this in maybe more detail. So let's say we have a characteristic equation. And I'm going to refer to the previous slide here for your information. Here, when I explain this story, I did the time simulations first. And then I mentioned that there are 3 characteristics: stable, margin stable, unstable. And I explained that with respect to the spectrum of the system. This is how I explain to you, but this is not how you analyze. The analysis is actually in the reverse direction. So let's actually look at how we actually approach the analysis. For the analysis, we start with a characteristic equation. We know it's retarded type, so we don't have to worry about the neutral system and all that additional conditions. Imagine somebody gives us a k and tau. They ask us, is this system stable? And imagine that you can solve all the S values that satisfy this characteristic equation. And those S values are characteristic roots. And you put them on the complex plane. Here's just a representative picture to kind of give you a visual connection. And as I mentioned earlier, it is very important to inspect, or to find out rather, when these eigenvalues will touch the imaginary axis for what tau values. And where will they touch the imaginary axis? And for what tau values will they touch the imaginary axis? Because that is a clue as to system's stability transition. Then, depending on where these roots are on the complex plane, we have 3 possible scenarios. They may be all on the left of the complex plane, half plane, then the system is stable. There may be a pair of eigenvalues on the imaginary axis, or they can also be on the origin. There can be one on the origin, and all the other eigenvalues are stable. They're on the left half complex plane. Or there may be at least one eigenvalue touching the imaginary axis or on the right of the imaginary axis. Then we have an unstable system. And based on this characterization, then we know that we expect very unique step response characteristics from the system. This is the way we're going to approach the problem and analysis. We will start with the characteristic equation. We will look for ways to understand whether or not the eigenvalues can touch the imaginary axis. If they do, what delay values, and that will help us understand the boundary between stable and unstable, which is that critical point. The green one is really what you want to understand, because this is the separator between a stable behavior and unstable behavior. So what parameters do I need to have such that I am at the border of losing stability? If I can understand that, then I can divide the parameter space on one side stable, the other side unstable. All right, so let's get maybe started with some considerations. Now, one may wonder, all right, here you have used a software package called Beef Tool, and what else can I do? You can actually use other toolboxes, and please just Google them, and I believe they're all online. And then you can use these toolboxes to reliably approximate the location of the system's rightmost roots. And if the rightmost root have a negative real part, you know that the system is stable. If it has a positive or a zero real part, you know it's unstable. Very good. Now, I don't want to mean that this is the only way to analyze stability. There are actually two main techniques in the literature when we seek to study stability. One is based on time domain techniques, energy-based. They are based on Lyapunov stability theory. The other one is the frequency domain techniques, which is what we have been discussing so far, because it's based on the spectrum of the system where the eigenvalues values are on the complex plane. It's an eigenvalue-based approach. That's what we have discussed so far. That's what we will discuss for the rest of this workshop. But I want to make sure I acknowledge time domain techniques because they're actually really powerful. And especially when it comes to problems of time varying effects, nonlinearities, and robustness problems, they are preferred, and they are the way to go. And one challenge we may face sometimes is when we convert these time domain techniques to linear matrix inequalities, that conversion process may add some conservatism, and the results of stability analysis can be more conservative. And we don't have that issue as long as we just work with LTI systems, and because the frequency domain techniques will be consistent with the Nyquist stability criterion. All right, so now let's provide a definition here. It's called spectral upser function. Spectral upser function is the real part of the rightmost root. And this function, you know, is continuous, meaning if delay is slightly changed, the spectral upser function will also move continuously. It's not necessarily differentiable, but it will be continuous. In other words, if the delay value from 0 is increased gradually, the spectral upser function representing the vertical axis that passes through the rightmost pulse, right, will continuously move to the right and to the left as the delay parameters is increased. Depending on the problem, it can move to the right, it can move to the left, it can move in either direction depending on the delay value and depending on the type of system one is analyzing. That is really important because if I am increasing delay from 0 to up to a certain bound, right, the only way I can destabilize the system is the eigenvalues continuously migrate on the complex plane and they eventually touch the imaginary axis. The only way the system can lose its stability is by having poles on the imaginary axis. And this also indicates, this property of continuity also indicates that by making small changes in the parameters, delay parameter or system parameters, a pole cannot disappear and reappear elsewhere on the complex plane. The poles have to actually migrate in a continuum on the complex plane as the parameter of interest is varied in a continuum. And therefore, the only way the system can lose stability or recover stability is the system's poles touching and crossing over the image axis. Once again, this is emphasizing one more time how important it is to investigate the presence of system eigenvalues on the image axis. And imagine that the controller gain is fixed as an example, and we change the delay parameter from 0 to a positive value, and we know that system eigenvalues are migrating on the complex plane, they are moving around, and if at least one of these eigenvalues cross over the image axis and migrate to the right half plane, then the system will become unstable. And if there are no eigenvalues on the right half plane or on the image axis, then the system will be stable. And of course, this also then implies that as the parameter of the delay is changed from 0 to a very large number, right? And we have stable and unstable behaviors of the system. For certain intervals of delays, the system will be stable. For some other intervals of delays, the system will become unstable. And it is possible that for even larger delays, the system may become stable again. And this is founded in the delay decomposition principle. And therefore, in some sense here, we are technically founding the whole stability analysis approach into two fundamental citations, one by Richard Tatko, 78, and the other one by Askoltz and Norkin in 73. All right, so let's take these three messages and then make them a little bit more concrete in terms of a systematic approach. We said that the crossings will happen on the image axis. Therefore, our first task is to find all the critical parameter settings at which the system has eigenvalues on the image axis. The second one is referring to how the eigenvalues migrate and they will eventually cross over the image axis. Therefore, we need to investigate in task 2 how the sensitivity of these imaginary eigenvalues over the imaginary axis. In other words, if we increase the delay values slightly, and as when the eigenvalues are on the imaginary axis for some delay value tau star, and if we increase the delay value just a little bit past tau star, will the imaginary eigenvalues go to the right half plane or will they go to the left half plane? If they go to the right half plane, they will favor more instability. They will add more unstable poles to the system. But there are situations that these actually imaginary eigenvalues, they can actually move to the left half plane. Therefore, they will actually reduce the unstable poles by 2 by moving 2 poles to the left half plane. So we need to investigate, right, what is the tendency of these imaginary eigenvalues as the delay parameter is increased with a small amount. And once we understand task 1 and task 2, then our goal will be to investigate how many unstable poles or eigenvalues we have on the right half plane as the parameter of interest sweeps from 0 to, let's say, infinity. And in an example, and on multiple examples, I'll actually present you this approach in bold, these three steps, task 1 and task 2, and in task 3 we have some type of what we call stability instability decomposition of the system. All right, let's take these 3 bold statements and move them here. I use a little bit smaller text font size here because we already showed them in the previous slide. And now in task 1 we need to find the parameter settings, critical parameter settings, for example, critical delay values for that will place the system eigenvalues on the image axis. How do we do that? Well, we start with the characteristic equation. We set S equal j omega, and we look for some critical values tau star that satisfy this equation for some omega star. That's what we should do. Find omega star and tau star satisfying this equation where j is the complex number. All right, and imagine a scenario like this one. So the left half plane is stable, so shaded, real axis, imaginary axis. And on the complex plane, imagine that for delay 0, and it's because it's symmetric, I'm only showing the upper half. We have a pair of complex poles, and they're in a stable domain. And imagine now we gradually start increasing delay value, and for some critical value tau 1 star, the eigenvalues will touch the imaginary axis at j omega 1 star. In other words, omega 1 star and tau 1 star satisfy the characteristic equation. And imagine we start increasing the delay past tau 1 star, and that when we do that, the system will be destabilized because the poles on the imaginary axis will migrate to the right half plane. This is associated with task 2 now. And imagine we keep increasing delay value, and it's actually it's also possible that these pole values, although they are unstable, they will actually turn around and they can come back and cross the imaginary axis one more time at a value omega 2 star for some delay tau 2 star. So now tau 2 star and omega 2 star together, they also satisfy the characteristic equation. And now as we increase delay tau 2 star just a little bit, these poles on the imaginary axis will actually go in the safe or in stable region again. The system will become stable again. So imagine we start stable in the beginning, and as we increase delay, we become unstable at tau 1 star. We are unstable, unstable, unstable. We touch the imaginary axis again. After that, we become stable again for a larger delay tau 2 star. There is an example of a stability reversal, as we say it. So the system is stable for 0 delay, and is stable up to tau 1 star, and it become destabilized up to tau 2 star, and larger than tau 2 star, it can become stable again. And it can then become unstable again, and these stable intervals also may repeat more than twice in some examples. So here we are kind of getting a sense of how this may work and how we can go about analyzing it. Start with the characteristic equation, compute the critical values omega star and tau star, and obviously sort these tau stars in the ascending order from 0 to some value larger than whatever threshold you want to apply for delay values, and investigate in what direction the crossings are happening, left to right or right to left, and then determine stable, unstable decomposition of the system with respect to delay. All right, so now let's look at one example to demonstrate task 1 and task 2 and the delay decomposition. This is a very simple example to get started. And let's say we are given a characteristic equation of this type. This is a closed system with an integrator and a proportion controller subject to a feedback delay tau. We set S equals j omega in the characteristic equation, and we look for solutions omega star and tau star. All right, in this case, obviously, this is quite a simple problem, and where the following manipulations are actually feasible. We can write this equation by using the Euler's identity, using trigonometric functions, and separate into real and imaginary parts. From the real part, we find that the cosine has to be 0 no matter what tau omega is. And from there, we know what tau omega has to be. And therefore, we can substitute that tau omega into the second equation and solve for omega. And from here, omega has to be plus minus 10. We always and often work with positive omega values. So, and the poles are in this case are symmetric. They are complex conjugate. So we can just work with the positive quantities. So omega equals 10. All right. So now, because omega equals 10, we can go back to the characteristic equation, substitute omega equals 10, and then solve for tau. For that, we need to take a look at the phase conditions on the complex numbers. Here, tan j has a phase of pi over 2, and then the second term has a phase of minus tau omega. From there, one can solve for tau. And if you do that, you have infinite many delay values for which the system has a pole at S equals j omega. In other words, the system will generate an S equals j omega eigenvalue for all these delay values, and the counter L goes to infinity. Perfect. So now we have solved our tau star values. I don't have a star here, but these are our tau star values, and our omega star is 10. Good. So now that's task 1. What did the task 2 want us to do? Task 2 expects us to study in what direction these imaginary eigenvalues tend to migrate across the imaginary axis. For that, we can calculate the sensitivity of S against the delay tau. So we need ds over d tau. Of course, there may be singularities, so one has to pay attention when we're using this formula, but in this case, there are no singularities that we need to worry about. So we can generate what we call a sensitivity function. Sensitivity function calculates how the eigenvalue S tends to change as we increase the delay just a little bit, tau. And we can actually compute this with partial derivatives by using the characteristic equation. So our sensitivity function is in this form. And of course, it's going to be complex because the movement of S can have a real and a complex component. It will actually move in some angle as the delay is perturbed. But from a stability point of view, only we care the horizontal movement of S, because that's when we know if it's on the left half plane or it's going to be on the right half plane as it moves when the delay is perturbed. We don't really care about its vertical movement because from a stability point of view, that is not really critical for us. Therefore, we need to take the real part of this equation. And if the real part is positive, it means the real part of S is increasing. Therefore, the eigenvalues are actually, they tend to move to the right half plane. That's a destabilizing behavior. If the real part is negative, on the contrary, the eigenvalues tend to move to the left half plane. That's a stabilizing behavior. So by computing this real part of S, we can determine the tendency of the eigenvalues across the imaginary axis. In this particular problem, for these delay values that we need to substitute in this equation, right? Because we need to put the tau star values in there, and omega is 10 because that's where the crossing happens. And if you plug this in and if you calculate, what we find is for all these delay values, the real part is positive. In other words, when the roots are at 10j, all of these roots will cross in the destabilizing direction and causing more and more instability for each pair of poles crossing the right half plane. All right, to summarize, now we can do a delay decomposition along the delay axis. Roots will touch the imaginary axis at s equals 10j, plus minus 10j, for all these delay values that we computed. And every time they touch, and every time we increase the delay value just a little bit past this tau star, they will actually go to the right half plane. So at every critical delay value tau L, two more poles, or just past this tau L value, two more poles will be introduced to the right half plane. So 2, 4, 6, 8, 10 poles will appear on the right half plane as we hit these delay values and pass them just a tiny bit. Therefore, we can conclude the following. When there is no delay, we know that the system is stable because the pole is at minus 10, negative. And as we increase delay value, the smallest positive delay is going to destabilize the system. And because all the other delay values will just add more unstable poles to the right half plane, the system can only be stable up to the smallest positive delay value, which is pi over 20. Therefore, the system is only stable for delays from 0 to pi over 20. Thank you so much, and we'll continue with some more fundamentals and basics in the next section of the presentation, and I'll see you soon.